That's right. So, hi Matt. Just give you a quick introduction. So we've got Matt Bridle, who is a certified training instructor from DULOS. He's been writing and delivering training courses for DULOS since 2007, specialising in digital design and verification, VHDL, System Verilog, Python, C++ programming for embedded systems. Since graduating from the University of Cambridge, BA Honours in Computer Science, Matt has been in the electronics industry for over 25 years. In the engineering support teams at ARM, he worked in the development of VHDL, Verilog and C-based hardware modelling technologies. As well as training and support for their customer base, Matt also worked for a number of years on the implementation of FPGA signal processing designs in VHDL. Thank you. Over to you, Matt.
Great, thank you. It's quite funny when they read that out this morning for my other presentation. I thought, oh, I'd forgotten I did half of that stuff. Thank you for coming. So we're going to be looking at improving your VHDL verification with OSVVM and UVVM. And this is kind of trying to do the same thing that someone would do with System Verilog, say, but do it in VHDL. And before we actually go there, I need to explain why we'd even bother to do that. So what we're going for here is a methodology based on constrained random stimulus and coverage. So traditionally, the question that we've been asking when we're trying to do verification is, does it work? And that's a very good question to ask. And the traditional way of working out whether it works or not is to stick some things in at one end and see what comes out the other and make sure that what does come out is what we thought would come out. And that is good, but it's not enough, because actually there's another very important question which we haven't answered at this point, and that is, are we done? So it's all very well having your tests and they all pass, but did your tests actually cover everything that we needed to cover in the spec? So when you go back and look, well, does this thing work? Can you point to a test and say, yes, I know this worked because I tried it over here? And that's the job of coverage. So coverage is looking at what has been covered, and functional coverage in particular, we're looking really at what has been exercised inside the design, particularly in terms of what values have been given to important nodes through the design. So, I mean, that could represent anything. In a CPU, it might be the instructions that have been executed, for example. But it's the sort of, it's looking at what has actually happened in there, and does it really test what we want to test? And if the answer to the question is no, then what do we do next? Well, we have to somehow go back and say, well, I want to modify the stimulus that I'm pushing into my design so that I've got better coverage. So I've got a better understanding of a better awareness, first of all, of how much of the design I've tested, but also so that it's actually hitting the targets more. So the case of I want tests that cover the extra 30% that I didn't get the first time, for example. My bag back here. And traditionally, again, the way to write tests is to sit down and type some stuff, and we write tests. And as designers of small functional blocks, you probably do that kind of verification all the time, maybe, or you would create a little test bench that would just test the things that you know about and do what we might call glass box verification, where you can see inside and you know what was hard, so you know what to test. But the thing is, once you've got a big system together, it's actually quite difficult to create what we call directed tests, so manually written tests that will cover what we want to cover, especially once we get through the later stages of the verification cycle. Because if we're in the situation where we, got kind of 70, 80% coverage, assuming you've got a way of measuring coverage at all, which is also something we're going to talk about, how do we actually think through what do I need to do to make a test, to test the stuff that hasn't yet been tested? And that's quite difficult to do. So again, quite a well-proven solution to that problem is to use constrained random stimulus generation. So at this point, rather than say, I want you to do this and then do that and then do this and do that, we say, okay, Mr. Simulator, can you please generate me some tests that where the values going in are, say, I want values of A between 0 and 100 and values of B between 50 and 200, but I want more values in the range 75 to 80 and this sort of thing. So we're saying we're sort of steering the creation of this random stimulus, and that's why we call it constrained random stimulus. So it's not just completely random, it's not just give me whatever you like, because there's no direction there. That would be a case of we'd probably still be as lost as we were. There's no guarantee that's going to give us better coverage. But if we have an idea of the sort of things we're looking to get out, we can direct our stimulus generation to give us the kind of stimulus that we want without having to sit down and manually work out what the next 10,000 vectors are supposed to be. So the idea is that we'll hit this top of the, this laser pointer work, this does, hit the top of the, okay, much there, hit the top of the curve there and actually stop when we have reached the peak, as opposed to stop when we just can't think of anything else to write. I should say that 100% here does not mean you've completely proven 100% of everything in your design works properly. That is practically impossible with anything apart from a toy design. What we're talking about is 100% of our coverage goals. So we define what our coverage goals are supposed to be according to criteria which have been agreed with the customers. And that's what we're hitting. So that's what we're aiming for, hitting 100% of those coverage goals. If you aim for 100% of everything, then you're going to be disappointed because it's just too difficult to do. So traditionally, I said traditionally a lot today, but you know, the kind of the way that this has been solved has often been through system Verilog and maybe UVM layered on top of that. But it's not the only way to solve it. And certainly for VHDL-based houses, it's not always a path that they want to go down, because a whole new language, and it's not a little language either. System Verilog is massive, and UVM is massive on top of it. So it can be much more sort of appealing for VHDL engineers to say, well, can we do this in VHDL? The answer is, in native VHDL, it's actually pretty difficult. There's no native support for coverage in VHDL. It doesn't have a way of measuring whether I've actually given the value 100 to this particular signal or not at any particular point in the simulation. And also, its random stimulus generation is fairly primitive. We've got the ability to create random numbers, but basically we've got uniform, and that's it. There's nothing much else there in VHDL. So there have been two different significant, probably others, but there are two significant efforts to try and give the same kind of functionality the system Verilog has natively in the form of VHDL libraries. And we're going to talk about both of these in parallel today. So the first of these is OSVVM, an open source VHDL verification methodology. And this was developed by SynthWorks Design and LDEC, and it's open source, hooray. It's a VHDL-based verification framework. Now, it has come from originally it was focused mostly on randomization and coverage. And since its original inception, it's grown to be more of a whole verification framework if you want to use it. As such, we've got utilities for doing randomization, coverage, error logging, we've got component libraries, scriptability, this sort of thing. Which is actually very similar to what we have in UVVM, the universal VHDL verification methodology, developed by Logic AS in Norway, and again, open source, released under the MIT license. And this came from the opposite direction. So they started off with a big verification framework, but they didn't really have any support for coverage and precious little for randomization. And they've added the coverage and the randomization support. So they've kind of come from two different opposite directions and are very much meeting in the middle now. So the functionality provided by these two libraries is very similar. And in fact, even some of the ways that they do it are very similar now too. So a little overview of some of the stuff that's in OSVVM, and I'll keep flipping between the two because we're going to be talking about applying the same concept in both of the two libraries. So a little bit about OSVVM's kind of at the top level. So we have constrained random testing, and we have functional coverage, which I've been talking about already. Error logging and reporting, because actually, again, VHDL's reporting mechanism, again, it's a little bit primitive. We've got assertions, we've got the report statement, but again, that's about it. There's no real way to say something like, Can we suppress certain types of messages? Can we fail if this certain thing happens? Not an assertion violation, but the trouble is that that has to be configured in the simulator. So if I want to actually crash out the simulation when I get an error, I have to go into the simulator and say, well, when I get an error, please stop the simulation, which is a bit untidy. I'd rather have that in my verification framework rather than having to add it to the meta level, as it were, and put it in the script. We've got some test bench utilities for doing things like working out when we finish the test. So UVM has the objection mechanism for doing that. VHDL didn't have a really good native way of doing it, although we can kind of simulate it. Creating clocks and resets, which again is something you could do quite easily in VHDL, but it's a bit tedious. And if I want a clock, do I really have to write the same code to generate the clock that I've done 10,000 times already? Well, we have that stuff in OSVVM already. Dealing with both files and dealing with logging into the transcript window at the same time, and what messages we send which where, and some types that are used for creating verification components. And I'll be saying this a lot, we have very similar things in UVVM. So this page actually looks a bit different, but actually we've just focused on different things here. They actually cover very similar ground. So stuff that we have in UVVM includes logs and alerts, very similar idea. We have the ability to have messages of certain severity. We can configure how the simulator handles them. We can configure where they go to the transcript, to the log file, and so on. We've got the kind of checks, awaits, barriers, synchronization. Also, UVVM adds a whole load of stuff about string handling as well, things like this. And again, VHDL is not very good at that side of things. Randomization, which, as I say, in UVVM started off quite primitive, but has now grown to be quite sophisticated. And as it says at the bottom with a big catch-all, and more. So, first thing we're going to have a look at is randomization. So randomization in both packages is done with a protected type. So I don't know how familiar you are with protected types in VHDL. They're a kind of poor man's class, really. You have a declaration of a type, which includes both methods and data, but there's no concept of inheritance. So it's a one and done. You can't then have a structure of, a structure of class inheriting from one another. So both UVVM and OSVVM use protected types in their kind of base random number generation. They both have a way of initializing a seed, actually use exactly the same method name to initialize a seed. That is, the seed is where our starting point is in our random number generation algorithm. Because we want to generate pseudo-random stimulus, doesn't mean we want every simulation run to look different. If I run my simulation and I've got 70% coverage, if I run exactly the same simulation again and it chucks out a different set of pseudo-random stimulus, I can end up with 65% coverage. That's not helpful. I want to have predictable pseudo-random stimulus so that every time I run it, I get the same thing. That's a bit counterintuitive because you're thinking, well, it's not random then, is it? Well, it was never random in the first place. It was pseudo-random. This is a computer, right? But the point is we do want it to be predictable unless we change something deliberately. So if I want to change the stimulus, I will alter the constraints. I don't want the machine to do it without me. So the seed there is the starting point, if you like. You can think of the random stimulus generation as just almost going through a list of numbers. That's not what it does, but you can think of it like that, and the seed might be a starting point in that list of numbers. You don't understand what the seed means. There's no way for you to interpret that. It's just you give a string and it picks a place to start. But the important thing is if you pick the same string, you pick the same place to start each time. So we can get our random numbers in a number of different formats. So we can get integers, and so we can get integer between 255 at the top here. So they both have methods to create random integers. We can also do something a bit more sophisticated than just giving a range. I can say, please exclude certain values. So I don't necessarily want every value in that range. I might want certain values to be excluded. I could also say, just pick values from the list that I'm giving you. And for both of them, what the method, so rand_slv for OSVVM and the overloaded rand method for UVVM, they both take an aggregate as one of their arguments, which is a list of values from which to pick. We can also ask for signed numbers rather than unsigned numbers, and we can also weight the distribution too. So we can say, please give me, for example, here, I want I'm weighting by 100 with my numbers between 3 and 5 here, as opposed to 10 with the number 2. The random seeds can also be saved and restored. So if I want to return to the point where I was a few moments ago, I can do that by resetting the C at that point. So I can grab the current state of my random number generator, store that, then sometime later come back and say, I want to go back to that point, please, if that's useful. So I'll show the UVVM functional coverage first, actually. So what we have here is, again, protected type-based interface. So these T cover points are our cover point type. So I need to explain what a cover point is. If you're familiar with the system very long, you'll know, but I'm going to go through it anyway. So a cover point is a description of certain signals, in this case, that we want to cover the values of. So our cover point here, T cover point for CP opcode, is the cover point for the opcode signal that you see at the top. That can take any value between, well, in integer terms, 0 and 7, because a 3-bit vector can represent those numbers. We always think in terms of numbers when it comes to doing coverage. There's no point in saying, oh, did I get an X there? Well, who cares? It doesn't mean anything, does it? So we screen out X's, Z's, U's, don't cares, all the rest of that stuff. And we just concern ourselves with the zeros and ones of it. So for opcode, there are 8 potential values. We want to record how many times we have seen opcode in our simulation. And if we don't see it at all, then we might consider that as being a coverage hole. So that's what that red ellipse there is on the value 4. We've never seen 4 occur during our simulation. Therefore, that's a coverage hole. That may mean we need to go and alter our constraints for our stimulus to direct them to sometimes generate that value. Coverage holes may also be a little bit more complex than that. I'll talk about later. But for now, we'll just assume that we get a hole if we don't get any values. We think about the storage for each one of these values as being a bin. So the idea is it's a bin or a bucket, and you have a whole line of bins or buckets. And every time you get a value 4, you throw a ball into the bin marked 4. So that at the end of it, you can empty the bucket and you can see how many times you got the value 4. So we refer to these things as bins, hence the CP opcode.add_bins. That's common terminology. The mode, you can see at the bottom there, what we've done is we've created just 4 bins because there are only 4 possible values for mode because it's only a 2-bit vector. This is one way of creating bins. We've simply said bin range, and we've said that we want values between 0 and 3. And the 0 at the end there means give me 1 bin per value that I'm asking for, as opposed to give me a specific number across that range. The OSVVM looks a little bit different, and that's because they've moved away from protected type. Protected types are the natural way to do this in VHDL in some ways, because they're a nice interface. And for those of us who actually did some object-oriented programming once, that's actually quite a nice way to work. But the trouble is, in the VHDL language, they're not very, you can't pass them around, for example. You can't use them as arguments to functions or ports on entities and things like that. You have to just have these shared variable things, which immediately that means global variables, and my alarm bells are ringing saying dodgy, dodgy. So the way that we use them is unfortunately a bit restricted. So although they're a nice idea, the VHDL language itself has some restrictions on how you can use them. And moreover, a lot of the simulators don't have full support for protected types. So actually, the fact that protected types are a good idea in principle, but a good fit for solving this problem, doesn't necessarily mean it works very well in practice. So OSVVM have now gone down another route, which they call the singleton. And the idea here is that we create a unique ID. So for CP opcode, we're going to create a new ID. So new ID is just a function call here. And that returns something of the type coverage ID type. And then when we want to add bins to that cover point, we say, well, we give it that ID as the first field. So it's a bit like doing object-oriented programming in C, where you had to actually pass in as the first argument the object that you were working with because it didn't have the support natively. But the advantage of this is that we're not then restricted in how we can pass these things around within the language. We have to wait for 0 nanoseconds here because we have to make sure that these two things update. If they don't, then we can't add the bins to them. Those won't exist yet. So CP opcode and CP mode will still be, will not be meaningful values. We can't add bins to them. So because those are signals, we have to wait for some amount of time. 0 nanoseconds will do because it only needs to be a delta cycle. In normal circumstances, I don't recommend people waiting for 0 nanoseconds. I try not to mention it at all when I'm teaching for VHDL because it's a recipe for people putting all kinds of unpleasant tricks. But in this case, it's justified. So that's setting up the bins for coverage. What happens? How would you actually measure what goes in? Well, we call a method or a function to actually sample data at a given point. Now, in System Verilog, you can do this automatically. You can set up a class or, well, yeah, not so much the class, that tends not to work like that, but with you can set up a cover point and a module, which will then sample automatically every kind of positive clock or something. But actually, when you move along to class-based verification, you tend to do it manually anyway, because you tend to be working in a transaction-based system, and you know when the data is ready to be sampled. So that's the principle we've gone with here in UVVM and OSVVM. So we have functions in the case of OSVVM, methods in the case of UVVM, which say right now, please sample what value is in this signal variable here and record it in the appropriate bin in this cover point. So for example, we look at that first line there that's highlighted. I cover CP opcode, so that's the cover point we're working on. The value is whatever's in opcode, but of course we're working with integers. Opcode's a standard logic vector, so I've got to do a bit of type conversion malarkey to get it to be an integer before I can sample it. That's just life in VHDL. So we convert it to an unsigned and then to an integer. Very similar thing happens in the UVVM sample coverage as well. You'll notice also that both of them have to put an interesting trick to work with a value that's just a scalar, because a scalar value can't be converted directly to a signed or an unsigned because it's not vector or anything, it's just a standard logic. So we create on the fly an unsigned vector whose only element, 0, is the value of the thing we're trying to sample. That's a bit grim, but there we go. It's what everybody does. We can create a bin structure which is more flexible than what we've been talking about so far. So far, I've assumed that what we want is 1 bin per value in the given range, but some values may matter more to you than others. It's quite likely that what you really want to do is check that for an 8-bit vector, you've at least sampled a few zeros, a few 255s, and then maybe split the rest of the range into 4 or something like that, have a distribution throughout the rest of the possible values. So there's quite a lot of flexibility in how we can create the bits according to what we want. So the first examples up there are the addBins method for UVVM and the addBins function for OSVVM. We're generating just a single bin. We just want 1 bin, we've called it B0. The second example, we're adding 2 bins for specific values. So in this case, 1 and 3. The syntax differs slightly, but the idea is the same. In the third example, we want to add 1 bin that covers a range of values from 4 to 7 inclusive. Doesn't include 7, this is not Python. So we have just 1 bin for that whole range. In the fourth example, we're creating 8 bins where we have 1 for each of the values in the range 8 to 15. So that differs because we haven't, again, the syntax is slightly different. So UVVM here, what we've said is in order to get 1 bin per value, we said 0 as a third argument in our range here. In our OSVVM example, to get 1 bin, we said get 1 bin, and the default is to get 1 bin per value. Those 4 bins, the fifth example that we have there, that's creating 4 bins across the whole range. So between 16 and 127 inclusive, we're dividing that into 4 parts. The two at the bottom are quite interesting. So the first one here is ignore bins. So there are some values you just don't care about. Maybe they're things which will never happen, and therefore you don't want to be reported as coverage holes. Or maybe they're things that you're just not testing in this particular run of your verification. So in that case, we could say, well, please ignore any values that occur between 128 and 254. The one at the bottom is a weeny bit controversial. That's an illegal bin. The illegal bin means if you get a value in there, then that just shouldn't have happened. So raise an error, start throwing your hands up in the air and say, there's a problem here. Now, the problem with doing that is that's not the job of coverage. Coverage is not there to answer the question, does it work? It's there to answer the question, have we tested enough? So if the coverage is trying to get in the way of saying, is that a valid value or not? There's a good argument for saying, just stay in your box. That's not really what you're there for. The checker should be handling that. And it could lull you into a false sense of security, or the coverage will handle whether you've got illegal values. But it's actually not done as comprehensively as it would be in the checker. So personally, I'm not mad keen on the idea of illegal bins. I would think just keep the coverage doing coverage. Here's a clever trick. Sometimes we care about combinations of values rather than just individual values. So for example, we could cross our two signals we've been looking at, opcode and mode. We seem to have lost the underscores from opcode now, but they're the same idea anyway. So along the bottom here, we have the 8 possible values of opcode, and up on the y-axis, we have the 4 possible values of mode. And if we just analyze the values of opcode, we already saw that there was a coverage hole for the value 4. So if we look at all the rows for the for a column indicated by 4, that means, well, we've clearly got a coverage hole there. But what we wouldn't have spotted just by measuring the current coverage of opcode alone is that actually we never get the value of 0 or 1 unless the mode is 0. So here we've got potentially a great big fat coverage hole if we care about the combination of opcode and mode. So we can create crossbins which say, please measure the combinations of these values. So we get a matrix out rather than just a linear line of bins. It's quite easy to do this. We add a cross coverage point which crosses one set of bins with the other. And we can either cross existing bins that we've created, or we can create bins to cross on the fly, depending on what is most suitable at the time. And you can also ask it to ignore certain bins, and you can create a bin structure specifically for each axis. So again, you might care about the boundary conditions more than the other values and so on. It's quite flexible. Of course, none of this is any good if we can't actually see what happens. So we have to report coverage at some point. And that's happily dead easy to do too. So in OSVVM, we have the write bin and write cov holes functions. In UVVM, we have the report coverage method, which we can give different arguments to see what we want to see. So the write bin or the report coverage non-verbose gives you everything. It says a report of what happened in every bin, but often you don't want to see that because it's an awful lot of data. Often you just want to see where the problems are. So you would ask for just the holes. So I'd say write cov holes or give me holes only. Now this is really cool. I really like this feature of these packages. This is called, well, OSVVM calls it intelligent coverage, UVVM calls it optimized randomization, but it amounts to the same thing. If I've generated a whole load of values and I've already filled up the bin for one value, I don't want to generate it again. What's the point? I'm wasting simulation time. So intelligent coverage or optimized randomization allows us to take into account what we've already generated in order to feed that back into the random number generator and say, don't give me any of those, I'm done. Just give me the stuff we haven't covered yet. So here's how we do it in OSVVM. We create our cover point, this cov here, wait for our 0 nanoseconds and add our bins. This simple example just has 256 bins across one bin per value. Then we use get rand point based on the coverage point. So the original random generation methods that I showed you at the beginning, they were just independent. They will generate you random numbers of the kind that you ask for. But in this case, we're saying, give me a random number that actually relates to the coverage that I've already experienced in that coverage point. And that means I'm not going to repeat myself. So in this case, a random value in the range 0 to 255 is not already covered. That means that my verification will take much less time because my coverage will converge much more quickly. A couple of other useful things on here, being able to get the item count, the number of data points that I've actually exercised on that coverage point. iCover here, remember, is how we sample the coverage, and is covered is a boolean which tells me when I've finished, when I actually got coverage that I asked for. UVVM, it looks a bit different, but it's exactly the same idea. So we create our bins across the range of 0 to 255. We say cover.rand, so it's a method called on the cover point itself, again, so it's related to the cover point, to again get a value in the range that we haven't yet covered. We give it this argument, no sample cov, to say, please don't add this to the coverage just because I've generated the data. So there's an option, if you don't give that, give a different argument, you can allow it to automatically update the coverage because you've actually applied the stimulus. The thing is though, you haven't applied the stimulus until you've done the stuff after this, so it's probably safer to do it this way. Then we sample the coverage as before, and again, we can ask whether the coverage has been completed. So coverage completed in this case with the arguments bins and hits. Have we actually hit our cover points and targets? I think this is really clever. So even system Verilog doesn't natively do this. Now, so far, we've been assuming that every value is as valid as any other one, or at least that every bin is as valid as every other one. That's not necessarily the case. So we might, for example, say that I want to create bins here with the values between 0 and 3, one bin between 0 and 3, but I want to generate values in that range at least 8 times. So in UVVM terms, that's min hits mapping to 8. In OSVVM, that's at least mapping to 8. But I might want to give other values with the same range, but hit them less times because I don't care quite as much. So here at the moment, I've got, so between 4 and 7, I want to hit that bin at least 4 times. And when I do this, that is what firstly determines whether I've got a hole or not. So it's only when I've hit the at least target that I actually have covered that cover point. And secondly, it affects how the intelligent coverage or optimized randomization is occurring. So that means if I haven't got 8 values in the range 0 to 3, that cover point is not covered. Therefore, it might generate me another value in there. But if I have hit 8, then it won't. Alternatively, I could define explicit weights for randomization. So rather than letting it work it out for itself, I could say, I want to bias the generation of the random numbers in this direction by giving weights. My personal feeling is if you're going to do that, you might as well use the randomization that isn't linked to the cover point because it doesn't really, it's not really linked in quite the same way once you've done that. So this is a more common way of working, I think. Okay, onto the logging mechanisms of OSVVM and UVVM. So I said initially that part of the trouble with VHDL's logging is it doesn't allow you to configure what you do with it. So you can basically have assertions which either pass or fail, but they are of 4 different severity levels, but you can't say what happens when you fail one of those assertions. So you can't say, for example, when you hit an error, please stop the simulation and tell me about it. You can only do that from the simulator itself. So you have to have a tickle script which does that and sets it up in advance. And okay, everybody's got a tickle script, but let's try and keep as much as we can in the actual VHDL code. So for OSVVM, we can log a message with the sensibly named procedure log. And log will give us a message which gives the sort of stuff that we'd expect from a VHDL asserter report statement. So we get the simulation time, we get the message text, we get the severity level, in this case it's always because we didn't give one, and we give the fact that it's a log as opposed to an alert. Alerts, something I'll go into in a minute. And we say that it's coming from OSVVM. So I can say OSVVM message 1, there we are. OSVVM message 2 with explicit always will also come out in my text. OSVVM message 3 with debug won't, because by default debug is not enabled. But I could then say, actually, enable those so that I want to see them in the log file or the transcript. And now if I put a debug message out, it will appear. And so will the info message because I've enabled those too. So we have nice fine-grained control according to what the kind of message is that I'm outputting. Here's some examples of UVVM log messages. We've got the ability to write out quite a lot of different formats of message in UVVM. So we've got, for example, a header, which gives us this nice little format with UVVM at the beginning and then a little kind of simulated line across the page, and it says what we're doing and so on. UVVM has different IDs for message to tell you what kind of message it is, and I'll give you a list of those a bit later on. UVVM also borrows the VHDL write procedure, so we can write to a line buffer and then send that to one of these log text block procedures, for example, and then that becomes the text that gets written out. So we don't necessarily have to construct a string in one go. And of course, here you can't really see the advantage of this because they're both strings, but the advantage of write is it's overloaded for lots of different kinds of values. So we don't have to do lots of type conversions to make the string in the first place. We can redirect to a log file as well. So again, OSVVM and UVVM do this differently. So in OSVVM, we have, we say transcript open and give a file name, and that automatically means that everything's going to go to the log file rather than the simulator's window. Then if we say set transcript mirror, that means it goes to both. So if you want it just in the window, you leave it as is. Want it just in the file, it says transcript open. You want it to go to both, set transcript open, and then say set transcript mirror. So in this example, the first message came out before we set transcript mirror. So we get both messages in the file, but we just get one message coming out of the terminal. And in UVVM, we can redirect log messages as well. So I can set the log file name and set the destination. So here I do it more explicitly and say, do I want it for console only, for log only, or both? And I can even get a big panel saying which IDs are enabled and which are disabled. This void is a curiosity of UVVM. For some reason, they're a bit allergic to the idea of having procedures that don't take arguments. So every time you get a procedure which doesn't need an argument, you pass it this special void thing. Here's some log message control in UVVM. So we can enable log messages of a certain kind. So for example, enable log message ID BFM, or ID BFM indicates it's a log message related to the BFM. Well, duh. We can disable log messages, and we can do that globally as well as per ID. And we can re-enable them, and we can also enable and disable them per component. So VVC is a VHDL verification component, and that is it is just a verification component, but written in a certain way that works with the UVVM framework. So we can enable and disable log messages coming from a particular VVC. We also, in both UVVM and OSVVM, have the concept of alerts as well as log messages. So an alert means, okay, this is a problem. There's no info alert. It's either a warning, an error, or a failure in OSVVM. And we have similar idea in UVVM. Actually, there are quite a few more levels of severity in UVVM. And there are a lot more ways to do this in UVVM too. So in OSVVM, we just have alerts. In UVVM, we have alerts. Warning, which is just like alert with the warning flag here, TB warning, which is like alert with the TB warning there, and so on. So just to save yourself some typing. And we do actually have a notes alert in UVVM. And part of the reason to have alerts is because it may mean that, as I said earlier, we want to stop. So a log message tends to just be for information. Here, if it's a problem, we may want to stop, or we may want to filter according to the severity, again, like we did with log messages. So we can set the stop count, for example. So OSVVM does it like this. The default stop count for a failure is 0. So if we ever get a failure, it just stops. But here what we've done is to say, we'll set the alert stop count for warning to 10, error to 2, and failure to 2. And then we've got 4 alert messages, and we've got 2 errors here. And remember, that means that we've reached our limit. So at that point, it will go, okay, on the second error, it goes, oh dear, I've reached my alert stop count. I'm now going to stop and say, it's failed. Notice that by saying the failure count for failure was 2, that means that even though I got one here, it doesn't stop. If I hadn't added that line, the first failure I got, that would have bombed out. I can also enable and disable like I can with log messages. So I've set alert enable for warning and area and failure to false in the first instance here. That means when I put this first alert out, nothing happens at all, and nothing happens on the second one, and nothing happens on the third one. But then when I enable them, and I can do that per message, but here I've done it globally, I then start actually getting them reported. We also have very similar alert control in UVVM, so I can set the alert stop limit, as with OSVVM. I can set, for example, when I hit 100 TB warnings, that's the time to stop. It probably is the time to stop if you had 100 warnings. Also, we can set the alert attention. So this is, again, saying I'm enabling or disabling, actually showing that on the screen or in the transcript file. And I can set in UVVM actually a separate log file for alerts from the one for log messages. And there are a whole bunch of special alerts and checks in both libraries. So for UVVM here, for example, this one check value checks that the value of the answer is 42. And it asks, what's the question? Those who've read the hitchhikers. Also, we can check that there are certain values in a certain range, so between 10 and 100, for example. Or I can check things like, has this signal here been stable for 9 nanoseconds? This stuff can be really useful. There's a whole bunch more of these utility functions. And they enable you to do things that you'll often want to do, or would previously have had to write 5 or 10 lines of VHDL to do every time. OSVVM has another bunch of these kinds of built-in alerts. I've shown some of them here. So alert if, that's just saying if that condition evaluates true, then we output the alert. Alert if not is the opposite. Alert if equal and alert if not equal are actually quite useful because they print out the actual and the expected value as well when you have the message come out. So you can use that for instead of an assertion. So I can say assert if not equal 2, 3. Well, obviously they're not equal, right? But if they were 2, this one was the actual expected value and that was the actual value, then it would print out not only that message and say it was an error, it would also print out what the values were that caused the failure. That's a useful thing. I promised earlier that I'm going to give you a list of UVVM message IDs. Well, here they are, aren't they exciting? You can express what kind of message it is. So it's not where it is in the hierarchy exactly. It's not how bad it was. It's philosophically what kind of message it was. So is it from a BFM? Is it from the sequencing tests? Is it a header message? This sort of thing. So you can give these message IDs, and UVVM also allows you to add your own by just adding them to the enumerated type and adaptations package. And OSVVM has an interesting way of handling alerts according to where you are in the hierarchy. So we have a hierarchical alert scheme where there's a base ID that's your top level, and you create an ID from your top level from that. So we say get alert log ID. We give the path name of where we are. So top tick path name. Tick path name is a built-in VHDL attribute. If you're not familiar with that, gives you the path name of where you are right now. Path tail is an OSVVM function, which is taking just the last part of that. And then we use alert log base ID, which is kind of a null. It's a starting point. And that creates us then, when we call get alert log ID, a unique ID for this level of the hierarchy. And then we can pass that down and create IDs for our children, which is really useful. So our architecture of top has 2 instances in it of this entity work.child. And work.child is passed in as a generic, this top alert ID to say this is your parent. So that top alert ID is then used as the base to generate a new ID for this entity child here. So that then enables us to have a unique identifier a unique hierarchical identifier for each place in our simulation hierarchy. So, for example, we might have a top here for this message, and then we might have, you can see it's indented inst 1 and inst 2, showing you that that's inside top. So this is quite a good way of getting a nice kind of graphical representation of how far into the hierarchy your issue necessarily is occurring. And there are variants of all of the alert and log functions which take an alert ID. So I can say alert ID message error instead of just alert message error, and that will then add the alert ID to the output. There are lots of useful utility functions for generating signals as well. Well, actually procedures in this case rather than functions. So UVVM here has gen pulse to generate a pulse on a particular signal, which is quite a useful thing to be able to do. They both have the ability to create a clock generator, or you can create a reset using this coordinate OSVVM, for example, and say how long you want the period of reset to be, and whether it's active high or active low. In a lot of these cases, they're concurrent procedure calls. If you've never met a concurrent procedure call, they're really cool actually. They're like concurrent assignments in the sense that they're like a process with just that procedure call in. So you can just put the procedure call in and it will do it all for you concurrently in the architecture. We also have synchronization in both libraries. We have barriers in OSVVM, which enable you to say, wait for a particular barrier to occur so that you can have all your verification components lining up at a particular point and waiting for a certain thing to happen. There are 6 predefined signals that you can do that, on, and you can also declare your own. UVVM has similar barrier features and also the ability to block and unblock flags, which is a more generalized version of the same thing. So you might have one process that waits on a flag to be unblocked by another process. And just to finish with, just a brief look at what the two libraries have in terms of the way that they structure their verification environments. So as I said at the beginning, UVVM started off with right, we have a verification environment for you. And OSVVM didn't have anything like that at all. It had the coverage and the random stimulus. UVVM didn't have that, and they've now really converged. So OSVVM now has a structured test bench. So we've got verification components, one per interface of our device. We've got test controllers, clock and reset logic, and there's quite a lot of built-in IP now in the OSVVM environment to enable you to build these things very quickly. And UVVM, similar idea, if anything more structured, because within our VHDL verification component, we've got separate ideas of a constructor, an interpreter which looks at what commands are being about to be executed, an executor which actually does them, and a terminator which finishes them. It's quite a prescribed way of working in UVVM. And very lastly, both packages have quite a range of IP related to specific vendors and so on. This looks a bit biased. Actually, OSVVM is catching up very quickly here. So I dare say that, in a very short period of time, this list will be as long as that one. But UVVM was in that game first, so they're slightly ahead at the moment. Okay, so I'm doing this on behalf of DOLOS, so you do lots of design and verification courses, also hardware design, embedded software, Python, AI, machine learning, and lots of other exciting stuff. So if you're interested in any DOLOS courses, come down to the bottom there and chat to one of our guys on the stand. Any questions? Yeah.
How's the performance of this versus UVM or Python version?
It's not something I've sat there and measured, to be honest. CocoaDB in Python would be less efficient because it's got to keep going across the simulator interface. So that would be the slowest in terms of simulation time. But of course, people who are going to use CocoaDB are doing it because they already know some Python and they don't want to learn a new language. And so they're saving in another way there. When it comes to system Verilog as opposed to VHDL, I mean, VHDL in general tends to be slower. But I haven't actually sat there and measured it, so I can't tell you for sure.
I guess which one would you recommend between OSVVM, UVVM, and OpenTV? I don't know.
So I'm not even allowed to tell you that because DLOS is vendor neutral. But even if I were, to be very honest with you, because they've converged UVVM and OSVVM, there's not much to choose between them. It really is a matter of style and philosophy. So I do have a preference, which I'm not going to tell you, but that's really just because of how it's written and how you use it rather than actually what it can do. So there really isn't much to choose from it.
Is there an industry trend?
Again, too early to say. I mean, there's people using both very much on the up at the moment. Quite a lot of people kind of rebelling and saying, I don't want to use System Verilog, I'm a VHDL engineer. So they're both really on the up. Okay. Thank you very much.
Thank you.
Well done for staying awake, by the way.
Do we have any questions online? No. Okay, that's the FPGA sessions concluded for today. Thank everybody for your patience, for your help, and for staying with us for the full day. Thank you. Till next time.